Okay, so we'll continue on the chapter on matrices, and hopefully we'll finish this chapter today. So last time, towards the end of the lecture, I was talking about this ellipse, right? So, or in more general, is the shape of the conic section, right? So, and I was trying to, right? So write down this equation of ellipse, right, in terms of a matrix form. Okay. So, and you can see that this is a row vector, this is a matrix, this is a column vector. So essentially, this is a dot product, right? So between this vector and this vector. And then in this case, so everything is nice, and you see this middle matrix over here is a diagonal matrix. Okay. So, and then I was trying to consider another ellipse, which is this red one. It's an ellipse also, but it's a rotated. Okay. So, and with this rotated ellipse, so it turns out that I told you that if you express it in an equation, okay, you not only that you have the x squared term and the y squared term, you will also have the cross term, okay, the xy cross term. Okay. So today, right, so we are going to actually, right, so give you an equation already in the first place, okay, which has the cross term xy term. Okay. So this is already a tilted ellipse. Okay, so just like this picture over here. Okay, and what we try to achieve here is that we want to try to find a new coordinate system. Okay, do a coordinate transformation. Okay, such that in the transformed coordinate system, okay, so this ellipse, the semi-major and the semi-minor axis of this ellipse will be parallel to the new x-axis and the new y-axis. Okay, so that's what we're trying to achieve here, right? So first of all, so if I have this ellipse equation, I write in the matrix form, is written like this, right? So if we are able to find a new coordinate system, right, such that the semi-major axis and the semi-minor axis are parallel to the new x and y axis respectively, then this matrix will become a diagonal matrix. Okay. So that is, right, so this is a process involving diagonalization of a matrix, right? So what we are going to do is the following, right? So this is where we start with, right? And then suppose I know that well, this matrix for sure can be diagonalized. You can see that this is a symmetric matrix, right? So suppose, okay, so I diagonalize this matrix, okay, such that the result is over here. So look at this line first, right? So if I diagonalize this matrix, right, so then this is what I have. Okay. And remember that this P is a matrix that is constructed by the two eigenvectors of this matrix, right? So this is the first eigenvector, and this is the second eigenvector of this matrix. And then, of course, this is the first eigenvalue, and this is the second eigenvalue. Okay. So, and in fact, well, you actually also know that because this is a symmetric matrix, and this is also the orthonormal set of basis vector, you know that this P inverse is actually also the P transpose. Okay, but now, right, so I know that this P inverse matrix P is equal to diagonal matrix. Okay. So then here, the next step, I'm going to write the equation like this, right? So you can see that what I do over here is that I put a P inverse here. So that what is P inverse? It's just an identity matrix. Right? So then I'm allowed to do that. Insert an identity matrix here because it changed nothing. And then over here, I again insert another identity matrix here, P inverse. Right. So now you can see that if I just look at this part, right? So P inverse this matrix P, right? So then that is my diagonal matrix, right? So, and what I also need to deal with, right? So let me just label it like this, right? So here I break it down into 3 parts. Right, so look at this one as one object, right? So and then this one as another object, this one as another object, right? So the green one itself is a diagonal matrix, right? So the green one itself becomes this. Okay. So now, what is the meaning of this P inverse xy? So this P inverse xy is that I am going to have a transformation matrix on this xy. Okay. So then this P inverse xy, I just call this x prime y prime. Okay, and this is given by this matrix P inverse multiplied by this xy. So then this is actually a coordinate transformation. Okay, so I call this x prime y prime. So and in fact, you see that this, if you take the transpose of this one, if I just write it over here again, so this x prime y prime is given by this P inverse xy, right? And I told you already that this P inverse, in fact, is the P transpose. Then if you go to take the transpose on both sides, then what you get is this. Right. Here, take the transpose on both sides, then you get this. Therefore, this one itself is my x prime y prime, right? And this is my also x prime y prime. Therefore, this whole matrix form now can be written like this, right? So in this new coordinate system, x prime y prime, this ellipse is written like this with just a nice diagonal matrix over here. So you can see that in the new coordinate system, right? So my equation of ellipse is given by this. So geometrically, what happened is that we actually use a new coordinate system, right? So you can see that the 2 green lines are representing the new coordinate system. Okay. And this new coordinate system is obtained from the old coordinate system by a rotation. Okay. So because in fact, this matrix is a rotation matrix. And that rotation angle, okay, you can clearly see from here because it is cosine theta, right? Sine theta minus sine theta cosine theta. So therefore, this rotation angle is actually given by the inverse cosine of 1 divided by -5. So then that is so much about the symmetric matrix and the orthogonal matrix. So then what we are going to do next is kind of a generalization to the so-called complex vectors and complex matrix. Okay. So I believe that you all have a basic concept of complex number, right? So if I have this complex number, z equals a plus bi, right? So then both a and b are a real number, and then this I is that imaginary number. And if I have this z, then on the complex plane, then I can label a point over here like this, right? So where this horizontal coordinate is given by A and the vertical coordinate is given by B. So then what I'm going to talk about the complex vectors and complex matrix is that in the entries of your vectors or matrix, I allow you to put in complex numbers. Okay, so that's all it means by complex vectors and complex matrix. But before going to that, okay, I want you to remember another concept that we are going to use is the so-called conjugate. Okay, if z is a plus bi, the z conjugate, which is z bar, what is it? Is a minus bi, right? And if you are going to take the product between z and z conjugate, okay, so what you have is a plus bi times a minus bi, right? Which is a square plus b squared. So z times z conjugate, actually, what does it give you, right? So actually, it gives you the square of the modulus of your complex number. Okay, so this length square is given by the z times z conjugate. Okay. Okay, so as I said, right, so if I want to have a complex vector or complex matrix, okay, all I'm saying is that suppose I have this vector over here, just a 2x1 column vectors. Okay. So that complex, give you an example of a complex vector is just that, like something like this. Okay, so this is an example of a complex vector. Okay. So for every element or every entries in this vector, I allow you to put in any complex number. Okay. So of course, it does not have to be all of them have to be a complex number, right? So because real number is also included. Real number is also a subset of complex number. Right? But anyway, this is an example of a complex vector. Okay. And of course, I'm not able to draw a picture on the XY plane on how it looks like, right? Because of this complex number. But this is the definition. Okay. And today in this lecture, okay, I won't be going to talk about when do we have this complex vector in physics. Okay, so but maybe towards the end of the course, if I have some time to talk about complex number, I will try to give you an example on when do we want to have a vector like this. But today we are just going to learn the basic operation. Okay. So now I have this complex vector. Okay, so what do I want to do with it? Okay, so in the last lecture, right? So the what did I talk about? Vector, right? Dot product. Dot product. So if I have a real vector, so when I take the dot product, I take this column, and then I take the transpose, right, and then multiply them together. So for complex vector, how do I take dot product? Okay, for complex vector, how do I take dot product? Okay, so let me show you how it is done. Okay, so this is my vector v. Okay, so if I'm going to do the dot product for this complex vector, what I need to do is, again, I'm going to write down my original vector v, 1 plus I, and then I also need the transpose. Okay, if I take the transpose, it will be 1 and 1 plus I, right? So, but not only that, after I take my transpose, I need to take the complex conjugate of all the elements, okay, in my vector. So then in this case, what it is? It's 1 and 1 minus I. Okay. So because the complex conjugate itself is just 1, right? So but the 1 plus I, the complex conjugate is 1 minus I. So this is how we take the dot product for a complex vector. So now if you go ahead and do this product, what do you find? So you find 1 square plus 1 minus I times 1 plus I. And 1 minus I times 1 plus I, 2. So then at the end, you have this 1 plus 2, which is 3. Okay. So this is how you take complex the dot product for complex vector. So that is what I did here essentially is this, right? So it's the V transpose conjugate, okay, times V. This is what I'm actually doing here. So you can see that even the vector itself contains complex number, right? So, but if I take the dot product with itself, it's still going to give me a real number because of the fact that I'm multiplying some complex number with its own conjugate, and that is always given real number. Okay, so but however, okay, so if I take a dot product between two complex vector, okay, so then what will happen? Okay. So if I take a dot product between two complex vector, okay, so that in general, the result might not be real. Okay, it could give you a complex number. So if I just let me just say this V1 is given by a first complex vector V1, V2, and then another vector V2, also a complex vector. I call this if it's W1 and W2. Okay. And if you are going to take the dot product, what you are going to do, right, just actually follow the same formula, is that for one of the vector, I need to take the transpose conjugate. Okay. And then for the other vector, I keep it at this. So that is, I'm going to have this V1 to be the transpose conjugate, which is V1 bar, V2 bar. And then the second one is just keep it as W1 and W2. Okay. And then you go ahead and do that V1 bar, W1 plus V2 bar, W2. So what about if I do this? So I'm doing this V1 dot V2, right? But what if I do V2 dot V1? So if I do V2 dot V1, so what I need to do is that the one up front is the one that need to be conjugate transpose, right? So this time, what I have is V2 conjugate transpose V1. So then I have this instead. Right. So, and this is equals to Z1 W1 bar plus Z2 W2 bar. Okay. But you actually realize that this is actually, although so now you can compare, right? So this one in general might not be equal to this one, right? But however, this one can be written as the following: Z1 bar W1 plus Z2 bar W2, and the whole thing conjugate. So then you can see that although this one might not be equal to this one, but they are actually always just related by a complex conjugate. That is, V1 dot V2 is equals to the complex conjugate of V2 dot V1. Okay. So here, I just give you more examples, right? So you can just verify it by yourself that you get these results. So then one more thing is that when we talk about dot products, right? So in the real vectors, so we use the fact that whether the dot product is being 0 or not to determine whether the two vectors are being orthogonal or not. So if I have now have two complex vectors, okay. So if I take the dot product between the two complex vector, and then I find that the dot product is 0. Okay, so then I will say that these two complex numbers are orthogonal, right? So is a natural generalization of the concept that we have in the real vector. Okay. However, right, so in the real vectors, we know that orthogonals essentially mean perpendicular, right? So, but again, here I'm not able to actually draw pictures of for the two vectors. Okay. So that I'll just call this orthogonal. Okay, I won't call this perpendicular. Okay, so then you know how this complex, you know, at least we know what a complex vector is. Okay, what about complex matrix? Then a complex matrix, again, is just nothing but that I allow the entries of the matrix to be complex numbers. Okay, so that's complex matrix. So, and in fact, we are going to focus on two special types of complex matrix. Okay. The first one that I'm just going to talk about is analogous to the symmetric matrix that we have for the real matrix. So suppose, right, so I have this n by n matrix. Okay. So what I'm going to do is to take the transpose of this matrix. Okay, so this is my matrix. If I take the transpose, so remember how to take the transpose, just the interchanging the row and column, right? So this 2 by 3 matrix becomes this 3 by 2 matrix, right? This is the A transpose. And then I do one step further. Okay, again, just like when we take the dot product, is that I'm going to take the complex conjugate of this transpose matrix. Again, what it means is really just that I'm going to look at the elements one by one, and then change all the elements to their complex conjugate. So you can see that from this A transpose, if I just take the complex conjugate for every element, it becomes this, right? So you can see that this 1 plus I becomes 1 minus I, this minus 2 minus I becomes minus 2 plus I, and so on. Okay. So then from this step to all the way to the last step, right? So I call this taking the conjugate transpose. Okay, conjugate transpose. And this conjugate transpose, okay, usually is denoted by, you can see this symbol here. This is a dagger symbol. Okay. So this dagger symbol, you see it again in your quantum physics class. Okay, so but this is a symbol that we use. So what it means, this symbol is really means that it's taking transpose and then taking a complex conjugate. So now, taking the transpose and the complex conjugate. Okay, so what properties does it have? Okay, so you can refer to this list of properties. Okay, so is that if you take the conjugate transpose for matrix A, and then you take it again, it becomes back to the original matrix. Okay. And also, right, if you have these two matrices add together, take the conjugate transpose is equals to individually taking the conjugate transpose and then add together. So these basic properties are essentially the same as what you have seen for the basic properties of taking transpose in real matrix. Okay. So then as I mentioned, I'm going to consider a special type of matrix, which is known as the Hermitian matrix. Hermitian matrix is that if you have a matrix that is equals to its own complex, equal to its own conjugate transpose, then I call this the Hermitian matrix. Okay. So again, this is a natural generalization of symmetric matrix. Okay. So for symmetric matrix, we have A equals A transpose. Okay. So now we have A equals A conjugate transpose. Okay. And this is an example. Okay. You can see that this is not a symmetric matrix, right? So because you can see that this number is not equal to this number, and this number is not equal to this number. But this is actually a Hermitian matrix, right? Because if you try to take the transpose right, and then take the complex conjugate of all the elements, right, so you can easily see that it is equals to this matrix itself. Okay. So this Hermitian matrix, right, as I said, is this generalization of this symmetric matrix to complex number. Okay, it has the same three very nice properties as symmetric matrices. So first of all, right, all eigenvalues are real numbers. So this is what we had for the symmetric matrix. Right? So it's quite might sound to you a bit surprising at the first sight, right? Because now I have all these complex numbers, right? If I'm going to find the eigenvalues, right? So it looks like I'm going to deal with a polynomial that contains complex number, but at the end, all the eigenvalues are a real number. Okay, but it is again because of the fact that you have the you have all this any complex number in the matrix always comes with this conjugate. Okay, so this is the first nice property. Okay, so the second nice properties, right, is that corresponding to different eigenvalues, right? So I have orthogonal eigenvectors. And then the third one is that even I have the eigenvalue with degeneracy, that is, if I have a repeated root, right, in my polynomial looking for the eigenvalue, then I am still able to find sufficient numbers of eigenvectors, okay, such that is, if I have an n by n matrix, right? So no matter how many eigenvalues are repeated, at the end, I'm going to be able to find n eigen vectors which are all orthogonal or orthonormal to each other. So in fact, for the first two properties, so I have given you the proof for the case of symmetric matrix. In fact, almost the same proof, okay, can be used to show the two properties over here. Okay, you can try it by yourself. Okay, how to just slightly modify the proof that are given in the lecture notes. Okay, for this case. Then the Hermitian matrix, right? So as I said, the generalization of this symmetric matrix. So the next, I will give you the generalization of the orthogonal matrix. Right? So remember what is the orthogonal matrix in the real case, right? So in the real case, the orthogonal matrix is that the matrix satisfies this Q transpose Q equals to the identity matrix, right? So and at that time, right, so I told you that essentially if we construct a matrix Q using an orthonormal basis set, right? So then you get this orthogonal orthogonal matrix, right? So remember that if this Q is composed of, let me just do 2 by 2. It's composed of two vectors which are orthonormal to each other, right? So if I do this, then this QT would be this, right? So it would be this V1T and then this V2T. And if I do QTQ, then the matrix I would get is V1T V and then V2T. I'm in this case, I'm still talking about real vectors, right? Just reviewing what I've said last time, right? So this V2T V1, and then this V1T V2, and then this V2T V2. And as I said, if this V1 V2 is not of a normal basis, right? So then the V1 dot V1 is 1, V2 dot V2 is 1, and then these two elements are 0. So then in the case of the complex number, right? So if I am going to construct a matrix again using an orthonormal set, right? So just like this. Right? So what I have is just a slight modification, right? So is that here I'm going to, instead of Q times QT, I'm going to consider Q times QT conjugate. So then in that case, this so then if you still get the identity matrix here, then I would say that this is so-called the unitary matrix. So unitary matrix is the generalization of orthogonal matrix for complex case. Instead of this QTQ equals identity matrix, here I have this U, the conjugate transpose U equals to identity matrix. And here are examples. Okay, so you can try to verify them by yourself. Okay. So the properties of unitary matrix, again, basically the same as the orthogonal matrix that we talked about last time. Is that first, the eigenvalues of the matrix, okay, may be complex, okay, but the complex modulus must be 1. Okay. And also, right, so if you use a unitary matrix to make a transformation for a vector, okay, so after the transformation, okay, so the magnitude of that vector is not changed. Okay, so finally, let's talk about diagonalization of a Hermitian matrix, right? So last time when we talked about the diagonalization of the symmetric matrix, so we have the one so-called the orthogonal diagonalization, right? So that is this A, which is the matrix that I have, which is a symmetric matrix, and if I am going to do orthogonal diagonalization, it's written like this. Right. So here for the Hermitian matrix, okay, so we call that the unitary diagonalization. Is that instead of doing this P transpose A P, okay, so here I'm doing this U dagger A U. Okay. So here let's look at one example. Okay, so this 2x2 matrix, first of all, you recognize that this is a Hermitian matrix, right? So if I want to diagonalize it, okay, how do we do it? Okay. So first of all, right, again, find the eigenvalues. Okay, so using this determinant, and then from here, you'll be able to find that lambda is equals to 3 or 0. Okay. So then just as a practice, okay, so let's try to see how to find the eigen vector for lambda equal to 3. So the process is actually still Gaussian elimination, right? But it's just that now you allow complex number to be in the game, right? So then for lambda equals 3, so the augmented matrix is what is this? Is 1 minus 3. And this is 1 plus I, 1 minus I, 2 minus 3. Right, so this is the augmented matrix that we have. And this is just go ahead and make this to be minus 2. And this is 1 plus I, 1 minus I. This is minus 1. Okay. So then Gaussian elimination, right? So I need to try to eliminate this the leading element over here, right? So what I do is that I take the first row and then multiply it by 1/2 1 minus I. Okay. Then what you get is that the leading element here become minus 1 minus I. Okay. And then the second element, you see that it becomes 1, right? Because 1 plus I times 1/2 times 1 minus I. Okay. And then the second row, okay, so I didn't touch the second row, so it's just this. Right. So then essentially, right, so this is just equals to, and then the second row can be completely eliminated. Right. So like this. So then what it tells me is that is minus 1 minus I times x plus y equals 0. Right. So, or in other words, y is 1 minus I times x. So then what is the eigenvector? Right. So if I call this x to be a free parameter c, right? So then y would be 1 minus I times c, right? So that's why my eigenvector is, right? So c times c 1 minus I, right? Of course, the c is irrelevant, so so then it just put it outside. Right. So then my eigenvector is just 1 minus I. Right. So then you can go ahead and try the other case, right? So for the lambda equals 0, so the answer is in the lecture notes, right? So but you can verify that you can get that. Okay, so that's so much for this part, right? So some special type of matrices. So now let's jump to the last part of this chapter, okay, so which is known as the system of linear differential equation again, right? So in chapter 4, right? So when we learn about the system of linear equation in the last part of the last chapter, right? So I actually already gave you a brief introduction on how to write the system of linear ODE, right? So in terms of a matrix form, and then and how to use the fact that if the matrix is a diagonal matrix, then the problem can be easily done, right? So I did briefly talk about that, but of course at that time I did not actually tell you how to do the diagonalization at all, right? So now that we know how to diagonalize a matrix, okay, let's look at how to actually solve the system of linear ODE using diagonalization. Okay. Right. So this is the system, right? So that we have seen in the last chapter, and now we are going to re-examine it, right? So in the last chapter, right? So the method that I actually taught is that I'm going to convert this two equations, right? So into just one second order ODE, right? So but here we are not doing that. So here we rely on the matrix, right? So this system, right? So can be written in matrix form, okay, just like this. Okay, so here, right? So this A11 is just this one, right? So this A12 is just this one, okay. And then now, okay, so I can just sometimes use this simplified notation. Okay, so this dx dt equals ax, but remember this A is a matrix, not a constant, and then this x is not just a single variable, but actually is a set of variables. So remember that in the last chapter, so I told you that, okay, if this matrix is a diagonal matrix, then this system can be solved immediately, right? So because, let me just try this. If this matrix is a diagonal matrix, right? So with a diagonal matrix like this, then this whole system is just written like this. Let me call this lambda 1 and lambda 2. Right. Right. So if this is, I'm saying, if this is a diagonal matrix, right? So then the system is just like this. So essentially, you can see that, right? So just it's not really, the two variables are not really coupled, right? So this x1 just depends on x1 itself, and then this x2 just depends on x2 itself, right? So then you can just solve the two individually, right? So no need to even write them as a system, right? So now, right, the reality is that, right, so this is not, right, so this is not a diagonal matrix in general. But now, okay, so we know that this is not a diagonal matrix, but it can be written as, right, so product of three matrices, okay, in which the middle matrix is a diagonal matrix, right? So because if I diagonalize this matrix, right, so this is what I do, right, and that is this matrix itself is written by P times diagonal matrix times P inverse. So now, if I just put this A matrix as this form over here, so then my equation becomes like this, right? So, and just a reminder, right? Remember, the P is of course constructed by the two eigenvectors of this A matrix. So then the next step is the key step. Okay, is that I'm going to move P to the left-hand side. Right? So if I'm going to move P to the left-hand side, so that means what I'm going to do is that this is gone and this is a P inverse. Okay. So now look at the left-hand side. P inverse times this derivative of this column vector. And this actually this P inverse and this derivative sign can be the order can be interchanged. Okay, so that means this P inverse can be put inside, right? Because this one just contains constants, right? So this is not just a number, but it just all contain constants. Okay, so that's why if I reverse this order of this P inverse and this ddt, then I can write the equation in this form. Okay. So now, on both sides of the equation, you can see that this P inverse x vector, right? Here also P inverse x vector. Okay. So I'm using this bracket to actually include this P inverse x vector just to emphasize that now I treat this whole thing as one object. Okay, so this P inverse x vector, what is P inverse x vector? Would be another vector, right? So it's a linearly transformed vector, right? So, but still, it would be a 2x1 vector, right? So after I do this P inverse x, right? So therefore, I can call this P inverse x, okay, as a new variable, a new vector or a new set of variable, which I call this U1 and U2. Then doing that, this becomes this, right? So, and then this one becomes this one. So now look at this system again. Now we know how to solve it immediately, right? Because diagonal matrix. Now this U1 and U2 are not coupled together, right? So just like this case over here now. Then at this point, we can immediately solve for U1 and U2. So after we solve for U1 and U2, right, the easy job is to do the transformation back to X1 and X2. Then we are able to solve the original problem over here. So this is the process, right? So this is what we have from the last slide, right? So write it out like this. Each of them very easy to solve, right? So this is just using the separation variable, right? So this U1 is some exponential function, U2 is also some exponential function. Okay. And this C1 and C2, of course, is some initial condition determined constant. Right? So now, right? So as I said, we need to go back to X1 and X2, right? So we know U1 and U2, and then now we just do the inverse transform, right? Using this P matrix, okay, to get to X1 and X2. And remember, what is this P? As I said, this P is constructed by the two eigenvectors of the system, right? So then you can see that this X1, X2 is given by this one. Okay. And then U1, U2, what are they? It's over here. Then I can just actually write it out as a sum of two vectors, okay, with these two functions. So now you can immediately see that the general solution, right, of this system is that the first eigenvector multiplied by this solution, right, and this solution, you can see this lambda 1, of course, is the first eigenvalue, okay, plus, right, so the second eigenvector multiplied by this second function, which is associated with the second eigenvalue. Okay. So then that is, right, so whenever you see this a system of linear equation, right, so basically you are just finding eigenvalues and eigenvectors, and then you are done. So just an example with some real number, okay. So if I have this system, okay, what is the first step, right? So first of all, right, so write it as the matrix form. Matrix form, okay. So I'm not going to repeat the process of diagonalization, right? So, but after you diagonalize this matrix, right? So, well, eigenvalue and eigenvector, right? So we just need to know the eigenvalue and eigenvector, right? So, I'll just give you the answer over here is that you get two eigenvalues. One is lambda equals 6, the other is lambda equals 2. Okay, and then the eigenvector for lambda equals 6 is 1, 1. Okay, and then for this lambda equals 2 is minus 1/3 1. Okay. So then the general solution is that you can immediately write down this one. So then the general solution is, yeah, if you remember this, you can just immediately write down this instead of thinking of the whole diagonalization process one more time. Okay. But you know that the reason why I can write it in this form is because of the diagonalization. Right, so then we are done. Okay. So of course you can also ask, so when I take the eigenvector, do I need to normalize them? you can, right? So if you for example, if you normalize this eigenvector, then you have an extra factor 1 divided by square root in front, right? So, but at the end of the day, right? So that one, whether you have a factor in front, will be taken care by your C1 anyway. So now, suppose if I want to solve an initial value problem. Okay, so suppose if I tell you that at t equals 0, x and y equals 2 and 1. Okay. Then how do you find the solution? Right. So this is an initial value problem. Right. So what it means is that you need to exactly figure out C1 and C2, right, given this set of initial conditions. Right. So, but that's not difficult, right? So then I just substitute, right? So this 2, 1 over here equals what? C1 t equals 0, right? So just C1 and then 1, 1 plus C2 minus 1/3 1. And remember, this actually can be written as this. Right. So then the C1, C2 can be just found by taking the inverse of this matrix, right? And then multiply by this initial value vector. So that's it. Okay, so then the next example, okay, is actually something that will be even more relevant to some physics problem. Okay, so and I will show you. Okay. So this time, okay, what I'm doing again is a system of a linear equation, but on the left-hand side, instead of first order derivative, now I have the second order derivative. Okay, you can see that. Okay. So, but you can see that the strategy of solving this system is exactly the same as we deal with the first order ODE. Right? So first of all, again, I write it in the matrix form. Okay. And then again, although this is the second order derivative, right? So, but as long as if we can make this matrix so to be a diagonal matrix, then it will be easy to solve again. Okay. So then that's why we use the exact same diagonalization procedure. Okay, so to convert this system, okay, so to look like this. Okay. Then again, now I have this U1 just depends on U1 itself, but U2 just depends on U2 itself. Then this system of this matrix system is written like this. Okay. Just two second order ODE which looks independent to each other. So then this one, right? So by itself, you know immediately how to solve, right? And this one also. So here I'm going to talk about two different cases now because you know that for the second order ODE, sometimes you have the exponential function, sometimes you have the sine cosine. Right? So it depends on the lambda 1 and lambda 2. If let's say first I consider this lambda 1 and lambda 2 to be a positive numbers. Okay, so in that case, then you have this general solution. So then you have this U1 and U2 found, then you are going to convert back to X1 and X2. Right, so after you convert back, this is what you are getting. So because this time I have this second order ODE, right, instead of first order ODE, then I have here, over here, I have 4 constants to be determined by initial condition. Okay, instead of just two constants. So now, if I have considered the second case, is that lambda1 and lambda2 are a negative number. Okay. So then this time you know that the solution is not exponential, but instead it should be sine and cosine. Okay. Then I write it in this way. So this might look a bit unfamiliar to you because usually when you solve the second order ODE, right, with this sine cosine, usually you write it this way. Right, in the last chapter, usually we write it this way. Right, but here you understand that this is equivalent to this. Okay. You can easily find the relation between this A1, B1 and this A and phi 1. Okay, so now let me give you one examples in physics that require us to use exactly this type of method. Okay, and this is an example in mechanics. Okay, so if you are going to take mechanics in the next semester, you'll see it again. Okay, but it's good to first get a taste of it. So you have all learned about simple harmonic oscillator, right? So simple harmonic oscillator, right? So if I have the simplest case where I have a fixed wall and then a spring and then connected to a mass particle, right? So and then you know that how to write down this equation of motion, right? So suppose this is the equilibrium position and then this is the displacement x, right? So in this case, the left and right oscillation, right, that equation of motion is given by this. Right, one single oscillator equation of motion like this. So now, what I want to consider is something more complicated. So what I have here is a system with two fixed walls on both sides. And then now I have two mass particles. And then they are connected by these three springs. Okay. So, and now suppose, okay, this is what happened at the equilibrium position, right? So, and then each spring has their own spring constants, okay? And they are all at their natural length initially, right? So now suppose you try to disturb the system, right? So to make them move. And then what happened is that, well, both particles will have their own displacements as a function of time, right? So this is which are the displacement from the equilibrium position for the first mass, I call this x1, and the displacement for the second particle from its equilibrium position, I call this x2. Okay. So I want to now set up the equation of motion. So you can see that this is, of course, more complicated problem than just one mass and one spring, right? Because if you look at this first mass over here, right? So it's under two forces, right? So first of all, is the spring on the left, but in this case, it's trying to pull it back to the left, right? So there is a force that is proportional to its own displacement x1. But also there is the second spring on the right, right? So this the force that acted on this first spring, right? So actually, right? So depend on whether this spring is stretched or compressed, like how much it is stretched or how much it is compressed. So then how much it is stretched or how much this is compressed does not depend on x1 alone. It also depends on x2, right? So therefore, now you can see that the equation of motion of this first mass, x1, won't be depending on x1 itself. It will also depend on the displacement of the other particle, x2. So similarly, right, so you consider the second particle, right? So you can see that, right, this spring, right, so will exert a force on it, right? So which is depending on x2, but also again, right, so this spring will act a force on this mass, again depending on both x1 and x2. Right? So then if I'm trying to, let me try to write down the equation of motion for one of the mass. Okay, so if I consider the mass on the left, right, so the m d square x1 dt square is equals to, first of all, the first force from the left spring, what is it? It's minus k x1, right? And then the second one is that, well, whether it's pointing to the left or to the right, depending on whether this spring is stretched or compressed, right? So if this spring is stretched, then the force is on the right, right? So if it is stretched, then what is the stretch amount? The stretch amount is x2 minus x1, and then multiplied by the spring constant of the mass in the of the spring in the middle. So and well, then you can see that if x1 if x2 minus x1 is smaller than 0, then that means this is a compression. Then of course this will automatically give you the minus sign. Okay, so then this is the equation of motion for the first mass. Okay, so let me just regroup the terms. Right, so that this is can be written as minus k minus k minus k plus k12 x1 plus k12 x2. Right. So similarly, you can find the equation of motion of the other mass, right? So then I just summarize it here, right? So now this is a linear system of second order ODE, and this is exactly what I'm going to do, right, is to make use of the diagonalization. Okay, so this is the matrix form. Okay, so I'm going to diagonalize this matrix. Okay, so again, the process are all written down over here. Okay, so finding the eigenvalues. Okay, so these, and then actually I call the square root of these two eigenvalues to be the eigenfrequency. Okay, because you know that the solutions are actually the sine and cosine. Okay, so then finding the eigenvectors for the two eigenvalues. Okay, this is what I got. Okay, so mathematically this is nothing new. This is just what I talk about. Okay, so now that's why the general solution is written like this. Okay, cosine solution, right, times the first eigenvector plus another cosine solution times the second eigenvector. So and now you understand why these two are all called the eigenfrequencies, right? Because it's exactly talking about the frequency of the oscillation. So let's look at just the first term. Okay, if I just forget about the second term, if I just look at the first term, is cosine at this frequency, right, times this eigenvector. This eigenvector is 1 and -1. What it really means is that the x1 and x2 is always off by a minus sign. Okay, so that is, of course, both of them are always oscillating, but always off by a minus sign. So that means they are moving the so-called out of phase. Okay, you can see that this is my picture. Okay, so they are doing a motion like this. Okay. So now, and the frequency of this motion, okay, is given by this omega-1. Okay, over here. Now, forget about the first term. Okay, if I just consider the second term, this is exactly the opposite. I have this 1, 1 instead of 1 minus 1. So that is, the two particles always move together, oscillate together. So then in the picture, I have this, right? So they move like this. And this omega-2, it has its own frequency again. So this omega-2, remember, is not the same as omega-1. So then these two, right? So each of these is known as a normal mode of this system. Okay. So this is known as the anti-symmetric mode. This is known as the symmetric mode. Okay. So then, in general, the system will be, the motion of the system is a linear combination of the two modes. Okay. It really depends on, again, right? So the initial condition. Okay, depends on the initial conditions. Then you can figure out this A, this phi1, this B, and this phi2. Right. So if you set up the initial condition appropriately, right? So you may be able to, you should be able to just make this A non-zero or B 0, or the other way around. Okay. But in general, right? So it can be a combination of the two modes. So this is the one physics example. Okay, so which you'll learn again soon. Okay. So here let's take a 5 minutes break. Okay, so here we come to chapter 6, which is known as the infinite series. First of all, before talking about series, I believe that you learn about sequence, right? So what is a sequence? A sequence is a list of numbers, right? So that are in order, right? So I have a list of numbers which I call A0, A1, A2, A3, and so on, right? So this is sequence. And what is a series? A series is summing up your sequence. Okay. So suppose I have a series that sum the first n term of your sequence. Okay. Let me call this Sn. Okay. So okay, be careful that there's a small n and a capital N. Right. So this S of capital N mean that you sum over the first capital N terms of your sequence. Okay. So I believe one of the one kind of the sequence or one kind of the series that you have learned is the so-called the geometric sequence or geometric series, right? Is that if I have the first term is A0, right? So then the second term is A0 times the ratio R, and then the third term is A0 times the ratio of this and square, and then so on, right? So this is a geometric sequence that I believe that you have learned before, right? So, and also, right? So if you want to sum a geometric sequence, so then you are doing this. Right. So in this chapter, we are actually not so much focused on what is the value after summing up this sequence, but instead we want to focus on whether this series, okay, so at the end will give me a finite number or not, okay. And okay, but before jumping into that, so let me again finish this. If I have this series, okay, how do you do the sum, right? So I believe that you have seen the trick is that if I have this series that I am going to write out all the terms, or how does it look like? So it's a naught plus a naught times r plus a naught times r square plus all the way to a naught times r to the n minus 1. Right. And now if I multiply both sides by r, then what you have is this, right? So then this a naught r plus a naught r square plus a naught r cubed all the way to a naught r to the power capital N. Now, if I subtract the two equations, right? So if I do 1 minus 2, then what you have is 1 minus r Sn equals all the terms on the right hand side. Well, these terms, all the terms on for 1 minus all the terms for 2, right? But now you can see that most of the terms will be cancelled, right? So this will cancel with this will cancel with this, and so on, right? So at the end, the only two surviving terms are this one and this one. Right, therefore, the right-hand side is simply just a naught minus a naught to the r capital N, right? And then S of n, therefore, is given by a naught 1 minus r to the n divided by 1 minus r. Right? I believe this is a formula that you have learned, right? So now, what we care about, of course, we are not going to just talk about geometric series, right? But what we are going to care about is that I want to sum infinitely many terms. Okay. So that is, I want to make n tends to infinity, right? So I want to find this limit. And I want to ask whether this limit exists, right? That means whether this limit will give me a finite number, a finite constant. So if that is a finite constant, then we say that this series, this infinite series, is convergent. Right? Otherwise, we say that this is a divergent series. So in this case, right, so can we see whether this is a convergent series or divergent series? So if I actually going to take the limit of this, so what you have is well, what you need only need to worry about is the r to the n, like this term, right? So r to the n tends to infinity. Then what is r to the n? So there are two cases, right? So if r is smaller than 1, right? So then r to the n will be 0. But if r is or well, magnitude of r, okay, smaller than 0, smaller than 1. But if this magnitude of r is greater than 1, right? So then I will give this then this series will just go to infinity, right? So then this is basically well, an example, okay, that we have this convergent series or this divergent series. Okay. So this geometric series is nice enough that we can really find a nice formula to calculate the sum, right? But what we are going to do in the following is that suppose the series sometimes can be quite complicated, that we don't really have a general formula to actually find the value of the sum, but still we have some way to tell us whether the series is convergent or divergent. Okay, so these are just the definition that I just told you, right? So let's look at the two examples of convergence and divergent series. Okay, although the geometric series already give you the example, but here I consider this series over here. Okay, so this is 1/2 plus 1/4 plus 1/8 and so on. Okay. And in fact, if you are still familiar with this geometric series, you immediately know that this is actually a geometric series, and with a0 equals 1/2 and this r equals 1/2. Okay. So you actually already know that this series is convergent. But let's look at it in a more interesting way over here. Is that I consider a square. This is a square of side 1. Okay, just consider this is a square plate, and then each time you are going to cut it into half and then take half of it. Right. So the first time you cut it into half and then take this half out. Then how much area do you got? You get 1/2. So then this is your remaining part. So for the remaining part, okay, so what you're going to do is again cut it into half and then get half of it. So then the second time you get 1/4. And then you are going to do it over and over again, right? So the third time you are going to cut this remaining small square into half again and then take this half. And then so on and on, and you realize that, right? So after doing this n times, so you are going to obtain the first n terms of this series, right? But you can see that no matter as you cut more and more times, you are approaching of getting the entire area of your original square plate. Okay. But you are never going to exceed it. At most, you are going to get the whole plate, which is 1. And that's why, right? So this infinite series, okay, so always will just tend to finite value, okay, which is 1. And this is a convergent series. So divergent series, okay, a very simple but famous example, okay, is known as the harmonic series. Okay, so what I have here, right? So instead, I have instead of 1 plus 1/4 plus 1/2 plus 1/4, here I have the denominator each time just increased by 1. Right. So 1 plus 1/2 plus 1/4, 1/3 plus 1/4, and so on. Okay. So this is known as a harmonic series, and we want to know whether this series converge to a finite number or not. Okay. So what is the similarity between this case and the previous case is that each term is smaller than the previous term. Right, so that's the similarity. We can see that the decreasing trend in this case is much slower. Okay, so than this case. Okay. So then here let's do a trick. Okay, so we are going to group the terms. Okay, so what I mean is that here, first of all, you can see that I have written down the first 16 terms of this series. Okay, just to show what's going on. Okay. So here I'm going to group the third and the fourth term as just one term. Okay, so you can see that the third and the fourth term, okay, add together, okay, has to be greater than 1/4 plus 1/4. Right, so that is greater than 1/2. Right. So and then the next, I'm going to group the next 4 terms together. Same idea is that these 4 terms add together has to be greater than, I just take the smallest term and then add them together 4 times. Right. So that's why, so that is this 4 terms add together is greater than 1/8 plus 1/8 plus 1/8 plus 1/8, right, which is again 1/2. Okay, and then here, right, so and then I group the 8 term together, and then again, it has to be greater than just taking the last term, the smallest term, and then add it to itself 8 times. So they can see that after groupings, right, so this first group give you 1/2, second group give you 1/2, third group give you 1/2, and then you need to do it over and over again. Right? So you can see that each time you try to group the terms, right? So you need more terms. Like you need 2 terms here, you need 4 terms here, you need 8 terms here. Next time you will need 16 terms. However, because this is an infinite series, okay, so then after you grouping or combining the terms, at the end, this is still a series that consists of infinitely many terms. Okay, so and because of that, right? So now I can write this series as just 1 plus 1/2, which is the first 2 I didn't touch, and then plus many 1/2. Okay, infinitely many 1/2, and that's why this series not going to converge. Okay. Going to give you infinity. Okay, so this is the example of divergent series. Okay. And question, and this is actually we'll deal with it next time, is that instead of having the plus for all the terms, what about I get this so-called alternating harmonic series? Right. So then for the second term I have the minus sign, the fourth term I have the minus sign, the 6th term I have the minus sign. So is it a convergent series or divergent series? Can I have 可唔可以俾多1-2分鐘? Okay, so in this case, right, so divergence means that at the end this number blow up to infinity, right? So but this is not the only type of divergent series. Okay, I can also have another case where the series at the end does not go indefinitely big, okay, but still it does not converge to one constant. And an example is over here. That, again, this is an alternating series. Okay, the magnitude of each term is actually the same, but I have this minus sign and plus sign alternating, right? So then if I ask you to do the sum of this series, right? So you will just keep doing this 1 minus 1 plus 1 minus 1, right? So then the sum, right? So as you increase n, is going to alternate between 1 and 0. 1, 0, 1, 0. Even you added many terms, right? As n tends to infinity, the sum will still alternate between 1 and 0. It does not blow up to infinity, but still, you cannot just give me a limit. Okay, so then this is the other case of the divergent series. Okay, I think I will stop here.